is an important parameter of a system. This is the gain of a system when frequency is 0. And that's why DC gain of a system is also called as the zero frequency gain. So suppose we are having a transfer function representing a system and we put s equal to 0 in the transfer function, then we will have the zero frequency gain, and that zero frequency gain is regarded as the DC gain of the system. So let's understand this with the help of an example. Given Gs equal to 2 multiplied with s plus 2 over s plus 3 multiplied with s plus 4, find the DC gain. So we are having a transfer function representing a system and we need to find out the DC gain of this system. So moving on to the solution, we are having two methods to find out the DC gain of this system. Let's go with method number 1. The method number 1 is comparison with the time constant form. If we convert this transfer function to its standard time constant form, we can find out the DC gain by comparing this transfer function with the time constant form. So in order to convert this transfer function to its standard time constant form, we need to take 2 common in the numerator, 3 common in the denominator from this term, and 4 common from this term. So we will have Gs equal to 2 multiplied with 2 multiplied with s over 2 plus 1 over 3 multiplied with 4 multiplied with s over 3 plus 1 multiplied with s over 4 plus 1. We have taken 2 common from this term, 3 common from this term, and 4 common from this term. Now if we solve this, 2 multiplied with 2 will be equal to 4 and 4 will get cancelled. So we will have Gs equal to s over 2 plus 1 divided by 3 multiplied with s over 3 plus 1 multiplied with s over 4 plus 1. Now we have this transfer function in the time constant form. And if we compare this transfer function to the standard time constant form, we can say the value of k is 1 over 3. So we can write k is equal to 1 over 3, which is equal to 0.33. And in the standard time constant form, the k represents the DC gain of a system. So we can say the DC gain of this transfer function is 0.33. So now we have calculated the DC gain of this system by comparing it with the time constant form. We have one more method to find out the DC gain of this system. So moving on to method number 2, for type 0 system, we can write the DC gain k as limit s tending to 0 Gs. As we have discussed, the DC gain is the gain of a system when frequency is 0. So we will simply put the frequency term, that is the s term, equal to 0 in this transfer function, and hence we can calculate the DC gain of this system. So substituting the transfer function Gs in this equation, we will have k equal to limit s tending to 0, 2 multiplied with s plus 2 divided by s plus 3 multiplied with s plus 4. Now if we substitute the limit s tending to 0 in this term, we will have 4 over 12, and hence the value of k is equal to 1 over 3, which is 0.33. But this expression k equal to limit s tending to 0 Gs is only valid for a type 0 system. We are given a type 0 system because there is no pole at the origin, and hence we can apply this formula. Now suppose we are given a type 1 or a type 2 system and we are asked the DC gain of that system, then what we will do? We cannot apply this formula. Surely we can apply the method number 1, that is the comparison with the time constant form, but we cannot apply this particular expression for a type 1 system. Let's understand this with the help of an example. Given Gs equal to 2 multiplied with s plus 2 over s multiplied with s plus 3 multiplied with s plus 4, find the DC gain. So now we are having a type 1 system here because one pole is present at the origin and we are asked to find out the DC gain. Now, if we apply the same expression, limit s tending to 0 Gs, then in that case, when we substitute the limit s tending to 0, then this term will become 0 and the DC gain will become infinite. But the DC gain of a system is never infinite. Surely we can apply the method number 1, that is the comparison with the time constant form. If we convert this transfer function to its standard time constant form, we need to take 2 common from the numerator, 3 common from the denominator in this term, and 4 common from this term. And then we can easily calculate the value of DC gain k by just comparing with the standard time constant form. So this will be the homework for you to find out the DC gain of this system by using the method number 1. I will discuss the method number 2 for this system. So moving on to the solution, for a type 1 system, the DC gain k is equal to the limit s tending to 0 s multiplied with Gs. So if we substitute the value of gs in this expression, we will have k equal to limit s tending to 0 s multiplied with 2 multiplied with s plus 2 over s multiplied with s plus 3 s plus 4. Now in this case, this s and this s will get cancelled, and then after that, when we will substitute the limit s tending to 0, we will have the limit as equal to 4 over 12, and we can find out the value of k equal to 1 over 3, which is equal to 0.33. We will understand the significance of this expression in chapter number 3, that is in the time response analysis. As of now, you can take this as a formula to find out the DC gain of a type 1 system. Similarly, for a type 2 system, we can have the DC gain k equal to limit s tending to 0 s square multiplied with gs. So in a type 2 system, we will have two poles at the origin, and this s square in the numerator will cancel the effect of those two poles, and then we can apply the limit s tending to 0 to find out the DC gain.